As Heather said, what we're going to talk about this afternoon is managing corn fertilizer nitrogen with stabilizer products. I'm going to break this presentation into two parts. First, we're going to talk about nitrogen management for corn, just some general aspects of it, and try to point out why it's important that we improve nitrogen management. And then the second portion of it will be dedicated to describing the results that we have obtained so far of work that we've been doing with some of the stabilizer products. Let's see here, right arrow. Okay, why should we try to improve corn nitrogen use? Well, as we all know, corn is the major nitrogen consuming crop that we produce in the region. We produce about 500,000 acres on an annual basis. And if you use about 140 pounds of nitrogen per acre that we supply that crop, we're putting out between 70 and 75 million pounds in the state of Maryland. Now, you've also, I'm sure, heard that corn is a relatively inefficient user of nitrogen, that its nitrogen use efficiency is estimated at around 50%. And because of this, corn is considered to be a leaky crop. So what is this nitrogen use efficiency? And what I have here is a chart that is based upon real data collected in Maryland, collected on a silt loam site. We've conducted research on N-rate response of corn for 4 years. Again, this was a silt loam site. Across the, get my arrow up there so you can see. Come on, it's not cooperating with me, the pointer. There we go. All right, across our x-axis, we've got N rates. On our y-axis, we have yield. You can see the curve. This is a normal nitrogen response curve. We typically see a curve of this manner. And what we're looking at is a site that has a yield goal of 160 bushel per acre. And the blue line there describes the nitrogen rate that we supplied for that yield at the 1 pound per bushel of yield goal that we have. All right, let's first look at the efficiency of nitrogen that we can get at low nitrogen rates. And that's over here on this side. From about 0 to 100 pounds, and you can see the green lines there, we do a pretty good job of responding to nitrogen. In fact, at 0 nitrogen supplied, we averaged about 70 bushel yield with no nitrogen whatsoever. With the next 100 pounds, we were able to attain a yield of approximately 130 bushel. At low nitrogen fertilizer rates, we're actually very efficient at using our nitrogen. However, we typically don't want to under-fertilize. We definitely don't want to under-fertilize. What we're hoping to do is reach that point where the line starts to flatten out. Now you can see that we've got our agronomic optimum nitrogen rate listed here. Agronomic optimum nitrogen rate is that point where 1 more pound of nitrogen will no longer increase yield. In this situation, we maximized our yield at 154 bushel, and we did so with 209 pounds of nitrogen. Now, we don't fertilize for agronomic optimum nitrogen rate. It's not cost effective. We try to fertilize with what will be an economic optimum nitrogen rate. And generally what we find, based upon what the price of fertilizer is, our yield goal of 1 pound of nitrogen per bushel of yield will pretty much fall within brackets, and I didn't draw the lines here, brackets that will describe the economic optimum nitrogen rate depending upon whether corn prices are high or low, and whether fertilizer nitrogen prices are high or low. It's at this point here when we try to attain yield where we've increased, or try to attain our yield goal of 160 bushels, that our nitrogen use really becomes inefficient. You can see that we added an additional 60 pounds of nitrogen, and what we realized was about 20 bushel of additional yield. If we fertilize higher, we would have even more inefficient use of the nitrogen. Why do we care? Well, for a couple of reasons that we've heard a lot about the last few years. One, that nitrogen loss is a contributor to non-point source pollution in the bay and its tributaries. And more recently, the focus has been upon the Chesapeake Bay Executive Order, the TMDLs that were derived from that, and within the counties in the state, the watershed improvement plans that have been developed. But I think there's a more important reason that we need to be concerned about managing our nitrogen as best we possibly can, and that's to protect what is a major investment in our corn production. With a potential loss of approximately 30 to 35 million pounds of nitrogen, if we lose 50% of that 75 million pounds that we provide every year, there's a lot of dollars lost. That can range anywhere from $17.5 to $32 million. Right, this is a slide that I like to use a lot. I've borrowed it from Jack Meisinger, and what it essentially shows you as we walk through it will be the fate of fertilizer nitrogen when it's applied to our fields. Now what we have here is a landscape, and our landscapes across Maryland can vary from relatively flat to, in some cases, it can be quite slow. Now of course our goal when we place nitrogen on a field is for our crops to take it up as best they possibly can. Now one thing that's very important to note in regards to nitrogen is that it's driven by hydrology. Everything that occurs out there regarding nitrogen is based upon the precipitation that we get, whether it be too much or not enough. All right, let's look at the two forms of nitrogen that can be supplied to the crop. First, we're going to look at is ammonium. Ammonium is nitrogen with 4 hydrogen ions attached to it. That gives it a positive charge, which is good, and we'll talk a little bit more about in a minute here. Now, ammonium applied to the surface of the field is subject to volatilization. It's subject to this volatilization because of this enzyme right here, urease. And what urease does is it catalyzes a reaction with ammonium that will remove one of the hydrogen ions. Remove a hydrogen ion from ammonium, you have ammonia, and ammonia is very susceptible to volatilization to the atmosphere. The hotter it is, the drier it is, the more ammonia loss you can have. Now, in the soil we have a lot of negative charges. Negative charges that are associated with the organic matter that's in the soil, and negative charges that are associated with the clay particles that we have in the soil. Negative charges are good. Remember that we've got this positive charge on ammonium. Well, if we get ammonium incorporated into the soil where these negative charges are, that ammonium is bound, and thus it's protected. However, this can be for a relatively short period of time, because once you get ammonium into the soil, it then becomes subject to the works of the soil microbes, and in particular nitrification bacteria. Now what nitrification bacteria do is basically feed on the hydrogen ions associated with the ammonium, stripping the hydrogen ions off. They're then replaced with oxygen, and you form nitrate. Nitrate has a negative charge associated with it. Now again, remember I said that nitrogen loss is driven by hydrology? If we have too much rainfall, we get waterlogged soils. One of the ways that we can lose our nitrate is through denitrification. Have an anaerobic situation, the oxygen start coming off of the nitrogen. Eventually you have N2 gas. N2 gas can be lost to the atmosphere. Another way, if we have too much precipitation, and particularly if we are on heavily sloped soils, get a lot of rainfall, we can have loss that occurs both in the form of nitrate and ammonium through erosion of nitrogen across off the site. But the way we lose nitrate the most in this region is through nitrate leaching. And why do we have nitrate leaching? Remember this negative charge that we have on nitrate? Nitrate in the soil, we've got lots of negative charges in the soil. You all are very familiar, I think, with magnets. When you put the same poles together, they reject each other. That's what happens with nitrate when it's in the soil. It immediately goes into the soil solution. Again, hydrology plays a factor. If we have too much precipitation, we can leach that nitrate down through the soil, out of the surface soil, into the subsoil, and away from the root zone for our plants. Eventually that nitrate can leach not only through the subsoil, but into the bedrock that's underneath our field, into the groundwater, and eventually it's lost again into our tributaries and into the bay. Now this surface applications of nitrogen, depending upon what kind of soil texture you have, lighter soils are definitely more susceptible to leaching loss of nitrogen than our heavier soils are, but they all will lose it by nitrate, and the amount of rainfall we get will determine how much nitrate is lost via the leaching process. So what can be done to minimize these nitrogen loss pathways? Well, we try to use good management practices for nitrogen to improve its retention. We can't hold on to all of it, but we try to do everything we possibly can to improve its retention. Those practices include choice of the source of nitrogen, and I'll walk through some of those different types of nitrogen and describe their pluses and minuses in just a second. Application timing is important, application method is important, and this last one, enhanced efficiency fertilizers and stabilizer products, is the focus of this presentation this afternoon. All right, let's look at the various nitrogen fertilizer sources that are out there. The first thing to remember is all of them are susceptible to loss. Anhydrous ammonia, very cheap source of nitrogen. In the Midwest, it is the primary source of nitrogen. 83% nitrogen, very economical. However, the disadvantage to anhydrous is that it does need to be incorporated into the soil, and I think you realize why. It is ammonia. You have to provide ammonia on the surface of the soil, and it's immediately going to dissipate into the atmosphere. So all anhydrous is injected into the soil. Typically, it's injected into the soil when soil temperatures have cooled off in the fall. You get fall applications, you get early spring applications. That's when a lot of nitrogen is supplied in the Midwest. Another form of nitrogen that we actually used a lot of 15, 20 years ago, ammonium nitrate. 34% nitrogen. It actually has very little volatilization potential. And the reason why is because ammonium nitrate has a positive charge on the ammonium coupled with a negative charge on the nitrate. So it's susceptible to very little volatilization. However, it is susceptible to leaching once it gets into the soil profile. Ammonium sulfate. This is an ammonium or two ammonium ions attached to a sulfate ion. In this case, you have little volatilization potential, again because of the binding that occurs between the ammonium and the sulfate. However, the disadvantage is ammonium sulfate is acidic, so if you're using any large amounts of it as your fertilizer source, your nitrogen source, you do have to pay attention to the pH of your soil. It's a wonderful source of sulfur and can help manage any deficiencies you have in that regard. However, it is a more costly form of nitrogen generally than the other forms that we're used to using. Now let's look at the two that we're more familiar with, the two that are available locally. The first is urea, granular urea, high concentration of nitrogen, 46%. However, the disadvantage to urea is it is in a granular form, so it is surface applied. If it isn't incorporated into the soil immediately, it's highly susceptible to volatilization because the urea will convert to CO2 and ammonia very quickly. Once it's in the soil, it is susceptible to conversion to nitrate quite rapidly. The other form that we're very familiar with in this region is the UAN, or the combination of urea with ammonium nitrate in water. We use a 30% solution in this area. It's a quite common source of fertilizer. Again, it's about 50% urea, so you have the same issues with susceptibility to volatilization, only at a lesser amount because of the lower concentration that you have than you would have with just the granular urea. Second management practice that I spoke of to help manage our nitrogen is application timing. What you're looking at here is a graph that describes nitrogen uptake, which we have on the y-axis, over a course of time. And this is from days of emergence of corn through the entire growth cycle. Early on in the corn growth, looking at this period right here, you can see that we have little nitrogen uptake. The majority of the growth, the nitrogen consumption that occurs is during this phase right here, approximately 30 days from emergence to about 90 days following emergence. That's when the majority of nitrogen is going to be consumed. Now, if you supply all of your nitrogen up front as a pre-plant, and we have excessive amounts of rainfall, and we've seen maize where we will get a lot of rainfall after planting our corn, you're subject to a considerable amount of loss, particularly if you're on the lighter, sandier soil. That's why the university recommends that we supply some of our nitrogen as a pre-plant and then the remainder as a side dress. And the side dress goes on about 30 days after you plant, or ideally at that V4 to about V7 growth stages for corn. However, once you put out that nitrogen, even by following the university recommendation of the pre-plant, about 25% of pre-plants followed by side dress, you really don't know what's going to happen the rest of the season. You fertilize at side dress time, hoping for the best the rest of the season, timely rainfall, good amounts of rainfall so that you'll maximize production. In those cases where Mother Nature doesn't cooperate with us, we have lower yields and we have more nitrogen that is susceptible to loss. Application methods is another way that we can manage our nitrogen, and some are better than others. The university recommends injection of your nitrogen. Again, the benefits you gain from injection is you incorporate that ammonium portion of your nitrogen into the soil and you bind it there. So you give it protection. Lots of folks prefer to put out surface applied UAN. They can cover more ground more rapidly by doing it this way. However, they are subject to both the volatilization loss pathway that can occur, as well as the loss of nitrogen after it's incorporated into the soil, either by rainfall or irrigation, to the leaching losses that can occur. And of course, the other method that is used is granular spreading of nitrogen. For those folks that are using granular urea, this is the only method that you have to get it out there. And we've already spoken about how susceptible to leaching or to volatilization loss that urea can be. All right, the fourth management practice that I mentioned was the use of either enhanced efficiency fertilizers or the use of nitrogen stabilizer products. Now, the first is a source of nitrogen that, when applied to fields, is less susceptible to N loss for varying periods of time, and I'll describe a product here in just a second so that you understand why. The second, the nitrogen stabilizer product, are additives that are used in combination with fertilizer, and what they will do is temporarily reduce either ammonia loss or nitrate loss by various mechanisms that I'll also walk through for you. All right. ESN, or environmentally safe nitrogen, is one of those enhanced nitrogen products that I spoke of on the previous slide. It's produced by Agrium Incorporated, and all it is granular urea coated with a synthetic polymer. This slide here, that's courtesy of Albert Sims from University of Minnesota, describes what happens when this ESN is applied to a field. It takes water to move into this polymer coating. You got a polymer coating that is around the urea. Water then moves into the inside of the granule and dissolves the nitrogen. The nitrogen then can dissipate out of the polymer and gets into soil solution. Now, this is all well and good. It's a very slow release type of fertilizer. The disadvantage to this system is that it is temperature controlled. Typically not a problem if it's used during our corn season. Where I've seen issues with it is where folks have tried to use it as a fertilizer for small grains. Temperatures are cold, it's dry, and the water doesn't get into the polymer coating and dissolve the urea. So you have a delay in response of your small grain crop in a situation like that. All right. As far as nitrogen stabilizers are concerned, there are two types. First are volatilization inhibitors. What volatilization inhibitors do, and I spoke about this when we had the slide about the fate of nitrogen sources earlier, is they impede the action of the urease enzyme, which catalyzes that removal of hydrogen ion from ammonia, turning it into ammonium, of ammonium, turning it into ammonia. Now, urease is a naturally occurring soil enzyme, so it is always there. All right. The other stabilizer product is nitrification inhibitors. What nitrification inhibitors do is impede soil microbes from converting ammonium to nitrate. Essentially what they are bactericides, or in other words, they are killing some of the soil microbes that are in close proximity to where the nitrogen molecule is, and by killing that bacteria, they then slow the conversion of the ammonium to nitrate. Commercial products that contain these various inhibitors include this product, Agritane. Agritane is actually NBPT. You can see the chemical formulation there to the left, and it's much easier to say NBPT than to repeat that. What NBPT is a urease inhibitor. NBPT has been tested for a long time. It is a proven urease inhibitor. However, it only will work for approximately 1 to 2 weeks. Agritane promotes itself as providing nitrogen protection to volatilization for 1 to 2 week period of time. N-Serve is actually nitropyrin. Nitropyrin is probably the nitrogen stabilizer product that's been around the longest. It is a nitrification inhibitor, which means it's a bactericide. It is used with anhydrous ammonia and has been used extensively with anhydrous ammonia for a number of years in the Midwest. The issue with N-Serve in our region, where we use UAN, is that N-Serve, if it was applied or somehow was on the surface of the soil, was subject to volatilization. So Dow AgroSciences actually formulated a version of nitropyrin, they called it Instinct, that is less susceptible to that volatilization process that occurs. So Instinct is the nitropyrin that is used in this region with UAN. Agritane Plus, another product that comes from Agritane International. This is another nitrification inhibitor. In this case, it's DCD, or dicyanodiamide, and you can see right here the cyan this helps describe how this works as a bactericide. You've heard of, I can't think of what I wanted to describe to you right there. But anyway, it is a bactericide. It kills some of the soil bacteria in close proximity to the nitrogen molecules in the soil and gives protection in that manner. Now, Agritane Plus is called that because it also contains the volatilization inhibitor NVPT that we spoke of for Agritane. So in this case, you're getting dual protection with Agritane Plus. You get volatilization inhibition, and you get nitrification inhibition with this product. Fourth product that I'm going to describe is Nutrisphere N. Been a lot of press about this particular product. What it is a maleic itaconic polymer attached to a calcium salt. I have no idea what a maleic itaconic polymer is. The mode of action remains proprietary, so we really don't know how it functions, but the company marketing this product promotes it as a season-long nitrogen management tool. All right, what I've built in here now is sort of a halftime, so that if anybody has any questions, we can address them, and then we'll go into the second half of this presentation where I'm going to talk about the research results that I've seen working with those four products that I just described to you. So what do I need to do here, Heather, to...
You can either click on your full screen button so that you can see the questions, or I can ask them. We've actually, your timing is perfect because we've had a few questions come in. One of the questions was whether Agritane is registered as a pesticide. You had described it as a bactericide.
Is Agritane labeled as a pesticide? That's a very good question, and I'd have to read the label to provide that answer for you. I can't say. I don't know.
We have another question. Yep, there's somebody asked if any producers that are using these products really see an increase in yield.
Well, I'm going to describe what I've seen in regards to their performance in the second half of the presentation. So I think that would probably be similar to what producers who have used the products have also seen.
Okay. Are there any concerns about these additives getting into groundwater?
None that I'm aware of, and I think that's primarily because, for the most part, their life in the soil isn't that long.
Okay, and there's a final question that I'm not sure I understand. Maybe maybe you will, or maybe we can ask for some clarification. The question is there any products available for NOP?
NOP. I don't know what NOP refers to, so I'm not going to attempt to answer that question. Organic certification, or any of these products, I would say no.
And that looks, that's all the questions that have come in now.
Should we continue on then?
I think so. I've just given it a few seconds and don't see anyone typing. So go ahead and continue.
On to the research component of this work. We've been looking at these products for the last 4 years. We've had funding from the Maryland Center for Agroecology, from the Maryland Grain Producers, as well as some funding that I got from the Agricultural Experiment Station here at the university to evaluate them. Had a graduate student who is doing his master's thesis research work evaluating these products. We essentially had 3 questions. The first one is, do the N stabilizer products work? And we know that nitropyrin, NBPT, DCD have been tested extensively, and I have no doubt that they work as they are described. The one I've been concerned about, and that's why I have here this, do they all function as advertised, is Nitrisphere N. There have been laboratory reports that indicate and have shown that Nitrisphere N does not function as a volatilization inhibitor. That in fact the volatilization of ammonia when this product is used with urea or UAN has been very similar to unprotected UAN or urea. We wanted to take a look at this in a field setting, and I'll describe to you how we did that. Second question we had was, and a lot of folks prefer to do surface application of UAN simply because they can cover a lot more ground more quickly during a period of time when they really don't have a lot of time to get their sidedress nitrogen out. Corn can go from the V4 to the V7, V8 stage in a relatively short period of time if we hit some wet weather along with that period of time. If they're relying upon injection, they feel that they're slowed down. So we're looking at whether or not surface applications of UAN with these products will function like an injected UAN as far as volatilization inhibition is concerned. The third question that we had, can N rates be reduced if an inhibitor is included with sidedress UAN? If you're going to use the product, there is a cost associated with it. It's in the neighborhood of about $10 per acre. So you would at least like to either reduce the amount of nitrogen that you're using, which would also be an environmental benefit, or see some kind of yield response associated with their use to cover the cost associated with their use. The way we've accomplished this work is, and I'll walk through this procedure slide here, we've used UAN as our nitrogen source. We have put out 20% of our nitrogen treatments prior to planting. The remainder of our nitrogen then went out as sidedress treatments, and it's at those sidedress treatments that we included our products. We had 3 rates of nitrogen, 160, 120, and 80. We included a control, which means we had no nitrogen whatsoever, including no nitrogen prior to planting our plots. The products were mixed with UAN and then surface applied at sidedress. We compared this with what we considered our check, which was the injection of UAN without products. Injection It is considered to be the gold standard, the best way of managing your nitrogen, so we wanted to compare to that process. We also looked at surface application of UAN without any of the products and make comparisons in that manner as well. Again, we were looking at the 4 products: Instinct, which is a nitrification inhibitor; Agrium, volatilization inhibitor; Agrium Plus, which is the dual-purpose product; and Nitrification, which also promoted as a dual-purpose product, but there are some questions about the performance of Nitrification. So, looking at the volatilization inhibitor performance, how did we go about testing for this? Well, we looked at the 3 that were being promoted as volatilization inhibitors: Nitrification, Agrium, Agrium Plus. We have a plot applicator that allows us to both inject into the soil or dribble the nitrogen onto the surface. We compared the products: surface application with injection and surface application of UAN with no products. The way we did this was with 1 liter PVC collection chambers. It was a passive process that we were using. What we did, you can see down here, we would put the PVC chamber over the site where the nitrogen was applied, either injected into the soil or dribbled on the surface. We would get over that site, put the chamber over the site. Chamber had a cork in the top of it, and then we would use these Draeger tubes. Draeger tubes are gas detection tubes that have a polymer rosin within the tube that, for whatever you're measuring, and in this case it's ammonia, will bind with the ammonia as you put the tube into the collection chamber. You have a pump. You can see right there on the hand in this center picture. There's a pump attached to the tube. You insert that into the chamber and put a vacuum on it and pull ammonia or whatever is in the chamber up into the tube. You can see here the discoloration that occurred. That indicates that there was some binding of ammonia with the polymer that's inside that tube. Now, these tubes are designed to measure a range of ammonia from as low as 0.25 parts per million to as high as 100 parts per million. Well, we did this on for a 2-week period following the side dress, and what we would do is on the first day we put it over the site where the nitrogen was applied. We took measurements that first day. We came back the second day, collected measurements, and then we moved the chamber, as you can see in this slide right here. We moved the chamber for the second day measurement, so we didn't remain over the same site each day. We wanted to get a measure of what was happening to that nitrogen as it was exposed to the surface and if it was getting washed in, if we had rain events or whatever. So we moved the chamber each day following the measurement collection. So what did we see? This is a bit of a busy chart, but I will walk you through it. On this axis here we have days from application, and it actually goes 7 days, as far out as 14 days we took measurements. On this axis here we've got the ammonia concentration that we measured with the Draeger tubes. Now, we had a control. That's this line right across here. You probably can't see it because it's at the 0 level. That was the control where there was no nitrogen supplied. And it remained at 0 the entire time. And that simply proves that we were able to measure nitrogen in these collection chambers with this technique. This line right here shows the amount of nitrogen that was, the amount of ammonia that was collected for UAN surface applied that had no product mixed with it. And you can see as we went from day 0, day 1, day 2, day 3, that we had a considerable amount of ammonia that we were collecting in the chambers. The orange line right here is our injected treatment of UAN. This is where you would expect to see little ammonia loss. However, we did see some as we moved out across the 2-week period, but it was much lower than what we saw with UAN that was surface applied. This line that pretty much parallels UAN is Nutrisphere N. The loss with Nutrisphere N across the 14-day period was very similar to the loss that we saw with UAN surface applied with no product. The red line right here is UAN that had Agritane Plus mixed in with it. It was also surface applied to the soil. You can see what we got there. For the most part, by day 7 we were seeing loss. But that's how Agritane Plus is promoted. It's promoted as giving you approximately 7 days of protection. During that time, you're hoping that you're going to get rain events that will help incorporate that ammonium into the soil and make it subject to a lot less loss. Now, the very interesting thing that occurred, and I want to point out these blue bars that I have here, those are rain events that occurred. We had rain events on days 1 and day 2 that totaled nearly 1.4 inches. This was a sandy loam site. What we found with those 2 rain events, we were not able to incorporate UAN into the soil enough to stop loss, as you can see it occurred with Nutrisphere N or with the UAN that was unprotected. That was a very interesting finding. Now this, again, was a very sandy site, rather porous soil, and we had fairly warm temperatures during that period of time. All right, 2010, same soil type, same description of products. Here's our check, remained 0 across the entire period of 2 weeks. The check was no nitrogen was supplied. Here's our UAN unprotected. There's our Nutrisphere N, the green line. Same loss pattern with Nutrisphere N as we saw with UAN unprotected. Here's our Agritane. Gave us fairly good protection until we got out here to about 7 days. The orange line down here is our injected product. We got our best protection with injected nitrogen. Agritane Plus functioned as it was described, giving you about 7 days of protection. Now, I'm only showing you a couple sites. We did this over a period of 4 years. What we did see at the sites, all of the sites, was a pattern that was very similar to this in regards to the performance of Nutrisphere N in comparison to the UAN surface applied. Agritane Plus functioned basically the same across all sites. Didn't matter what our soil type was. We saw basically the same pattern. Okay. We also wanted to see if we could verify whether or not we were getting urea conversion to occur. And this is sort of a novel technique that was used, a rather trying technique for my graduate students and technicians, I guess I should say, and you'll see why in just a second. But what we did was we collected soil samples at the same time that we took our chamber measurements for ammonia. Collecting them from the plots, collecting them from the area of application. We then froze those soil samples immediately, and we kept them frozen even while we were preparing them for analysis. And by that, I mean this. We kept them in a freezer, minus 16 degrees centigrade. In order to prepare them for the analysis or for the extraction, we had to grind the soil samples, and that grinding occurred in this minus 16 freezer. And these two guys are actually looking pretty happy at this point in time, but I think that was at about the time they ground the last sample. Very, very trying process. But if we would not have kept the urea frozen, it would have been subject to conversion. The urea would have been subject to conversion to ammonia very rapidly, and we wouldn't have been able to measure the urea concentration. So what did we see? with this. This slide right here I just described to you. It was the volatilization loss of ammonia that we measured in 2010 at Beltsville. This slide here is the measurement of urea that occurred during the 14-day period. Now you'll notice by 7 days, no matter what product we were measuring, whether it was the surface applied UAN, Agrium Plus, the injected, our check, or Nitrisphere N, by 7 days all the urea had been changed. Let's just look here at day 1. Yellow bar is UAN dribble. Red bar, Agrium Plus, higher concentration of urea. The black bar is the injected treatment. Green bar, Nitrisphere N. As we move on through days 2 and day 3, what you see for UAN surface applied and Nitrisphere N as they have dissipated or converted to ammonia pretty rapidly. Agrium Plus, this red bar right here, is maintaining the urea form quite well until about day 7. Day 7 is when we saw volatilization loss of ammonia with Agrium Plus starting to increase. So it's working for about 7 days, as they described. You're also probably thinking, well, heck, the injected treatment had its urea converted quite quickly as well. Now, it did, but that was not the urea being converted into ammonia and lost. That was urea converted to ammonium, converted to nitrate. So you're seeing how quickly that urea can be changed into a nitrate form with the injected treatment. All right. We're also measuring the performance of the nitrification inhibitors. We're doing this in 2 ways. We have pre-plant and post-harvest soil samples that we've collected to a 2-foot depth. What we're doing there is measuring the amount of ammonium, nitrogen, and nitrate in the soil and comparing among the treatments, Now, what we're hoping to see there is if a product slows conversion of ammonium to nitrate, is there a conservation effect that will result in a higher soil concentration in the fall. The other thing that we did was take SPAD measurements starting at reproductive growth or at tasseling, and taking them periodically. These are plant measurements during the season. What we're hoping in this case is that we can use chlorophyll or changing chlorophyll, and it's very closely associated with nitrogen concentration in the plant. If we can use this as an indicator that perhaps nitrogen depletion is occurring within the plant, and if we make comparisons among the nitrogen stabilizer products with the unprotected nitrogen, maybe we can see something there as well as far as a season-long protection that might be occurring. Now, at this point in time, we're still analyzing that soil data and SPAD meter reading, so I don't have that information for you, but please do stay tuned for the results. Those should be, as Patrick Watkins, my grad student, finishes his work here and the next year writes his thesis, we will have that data. All right. So what effect did these corn stabilizer products have on yield? And in this case, what are we looking for? Well, 2 things. One, did the stabilizer products at a reduced rate produce comparable yield to UAN injected at whatever the yield maximizing rate was for a location? What this would do is indicate both a cost-saving benefit for the farmer as well as an environmental benefit in that you have less nitrogen out there that potentially can be lost. The other question we had is, can a stabilizer product at the same nitrogen rate produce comparable yield to UAN injected? What we're measuring in this case would be whether surface application of the stabilized UAN can be considered a comparable practice to injection of UAN. In other words, if you want to surface apply your nitrogen and use a stabilizer product, you probably would, or you may be just as well off as getting it injected into the soil? Those are the two questions. What have we seen? 2008, at 2 locations, we maximized our yield that year with 160 pounds of nitrogen with the injected treatment. What we saw that year, and it looked great with this first year data, all the stabilizer products at the reduced rate, 120 pound rate, when we compared it to UAN injected at 160 pounds N per acre, produced comparably. In other words, we got a reduction in nitrogen rate. We got the best of both worlds that year, cost savings and environmental benefit. However, you don't base decisions upon 1 year's data. Yield response in 2009, each location was different. Beltsville was impacted quite severely that year by drought, produced very little yield, and we had really nothing to compare. At Poplar Hill, we maximized our yield at 160 pounds of nitrogen per acre. In this situation, none of the products at the reduced rate had comparable yield to UAN injected. In other words, we did not see what we saw the first year. There was no rate reduction. What we did see was that 3 out of 4 of the products at 160 pounds of N per acre had comparable yield to UAN injected at 160 pounds. In other words, in this case, we had surface application was a practice that would be considered comparable to the injection of UAN. 3 products, I should add, that gave us this response were Agrium, Instinct, and Nitrification. At Clarksville, we maximized our yield at 80 pounds of nitrogen per acre. We actually saw yield enhancement with a product that year. Instinct at 80 pounds N per acre exceeded our UAN injected at the same rate. 3 of the products at Clarksville at the 80 pound rate yielded equal to UAN injected at 80 pounds. So what we determined was that surface application was comparable to injection. 2010, at Beltsville, we maximized our yield with 120 pounds of nitrogen in the injected treatment. Instinct, at 80 pounds of nitrogen per acre, had yield comparable to UAN injected at 120. We had an N rate reduction again. And both Agrium and Instinct at 120 pounds of N had comparable yield to UAN injected. In this case, surface application was comparable to the injection technique. At Poplar Hill, we maximized yield with injected UAN at 120 pounds. However, at Poplar Hill, none of the products at either 80 or 120 pounds of nitrogen had yield comparable to UAN injected at 120 pounds. So we had no rate reduction, no surface application in this situation. And at Clarksville, we saw no N rate response, so we were unable to make comparisons. And in 2011, we saw a similar response across all 3 locations, so we've looked at things averaged over the locations. In this case, our UAN injected maxed our yield, or we maxed yield at 160 pounds of N per acre for UAN injected. There was no rate reduction benefit with any of the products. Surface application for only one of the products, in this case it was Agrium Plus, was comparable to the injected application, and the other products provided no benefit whatsoever. So what does all that mean? Well, let's go back over the questions we started with that were the objectives of this research. Question number 1, do the stabilizer products function as advertised? Volatilization inhibition. Agrium Plus had shown protection for about a week when mixed with UAN and surface applied. This is how those 2 products are promoted. Nitrification is promoted as a volatilization inhibitor. It has functioned the same as UAN surface applied with no inhibitor. It does not provide any volatilization protection. It is not functioning as it is promoted. It is not a volatilization inhibitor. far as nitrification inhibition, we're still working on those assessments. Second question, when surface applied, can these products used with UAN substitute for UAN injected, which is the gold standard? Surface application of UAN with a proven stabilizer product, and I should emphasize proven. If a proven stabilizer product is used at corn side dress, it can be and should be an accepted management practice. And the last question, what effect do these products have on corn yield? None of these products at a 25% reduced N rate have consistently produced a comparable yield to UAN injected. We have seen on occasion, Instinct was an example I can think of, where we did get a good response. I'm sorry, let me back up on this again. First of all, none of these products at a 25% reduced nitrogen rate have consistently produced comparable to UAN when it's injected. Only one time with one product have we seen yield improvement. Do not expect yield enhancement with these products. They're not yield makers. They are nitrogen management products. That's how they should be used, and if you're going to use them, use proven products. And with that, I thank you for your attention. I'm within my hour, and if there's any other questions, Heather, I will be happy to try to answer them.
One of the questions that came in was asking whether Agrium Plus is cost effective, and I think you kind of touched on that at the end there.
Question is Agrium Plus cost effective? I would say yes, because you're buying insurance. There's no guarantee that if you use the product, you're going to have the weather conditions that are going to cause nitrogen loss either by volatilization or nitrification loss. However, you have no idea what the weather's going to be prior to putting out your nitrogen. So the use of a product to protect your nitrogen, I think, is like buying insurance. If you're looking at cost effectiveness to be measured by a yield response, that's not what these things are made for.
So basically, if you do get the Agrium Plus and you put it out and it rains, it maybe wasn't worth the investment, but if you put it out and it doesn't rain until day 6, then it was well worth your investment? Is that what did I take that correct message away?
Yes, in regards to volatilization, yes, that's how it would work. If you put Agrium Plus out and it rains within a day or two, you're still getting nitrification protection with it, nitrification inhibition. How long that's going to function for you, functioning as a bactericide in the soil, it probably is also relatively short-lived, maybe a week or two, but you're gaining some protection of that conversion of the ammonium to nitrate in the soil. And then if you're on real sandy soils, and I think if you have real sandy soils, that's where these products can provide even more benefit for you.
Okay, great, thanks. We do have another one. Can the multiple application through fertigation beat these additives or even injection? Okay, so if you're applying nitrogen multiple times.
Multiple times during the season. Fertigation is an excellent approach to managing nitrogen, and that would be a better way of managing it than using nitrogen stabilizer products. I guess the second part of that question is, does it beat even injection? I'd say yes.
Okay, I see we still have a bunch of people with us. Does anybody else have any other questions, or are y'all looking out the window, getting ready to bust out of there for the weekend?
All sleeping. Time to wake up. Everybody go home now. It's 5 o'clock, 5 o'clock somewhere.
Okay, we've got another question that came in. On the test sites with 25% reduction and the additive that showed equal yield results, was a control of 25% reduction without the additive tested?
Let me make sure I'm following this question. On the test sites with 25% reduction and the additive that showed equal yield results, was a control of 25% reduction without the additive test? Yes. Yes, it was. Probably want to know how it performed as well. The performance we had with UAN surface applied bounced all over the place. We saw times when we definitely had yield reduction with UAN surface applied. We saw times where at our max yield, UAN unprotected compared to injected, or UAN unprotected compared to one of the stabilizer products, we had comparable yield. It was all over the place. What's that?
The non-impact of rain.
The non-impact
Okay, we've got another one.
of the rain event is surprising.
Yeah, go ahead. You can.
This had no impact. That was very surprising to me, because one of the things I tell farmers is that if you can get your nitrogen, in fact, if you can time getting your nitrogen out there a day or two prior to a rain event, and if you can get a ½ inch to an inch, you should be in good shape as far as incorporation into the soil. This particular site had very sandy soil, probably more like probably a loamy sand rather than a sandy loam. Quite porous, and we had some hot weather following the rain event. So I guess it was just dissipating up through this coarse soil and being lost. We did have other sites, silt loam soil, where we didn't see this effect. We saw the ammonium move into the soil, and we did not see the volatilization loss similar to that slide that I showed you. But I thought it was rather interesting, and I wanted to share that slide with you.
So do you think that soil type influences
Soil
how
type has
these
a big
products
effect
work?
upon how these products